All right, welcome. If you're gearing up for your GCSE Physics exam, you are in exactly the right place. We're about to do a super focused session on a topic that comes up all the time, describing motion. Trust me, getting this stuff down is a massive step towards nailing that grade you're after.
Okay, so here's our game plan. We're going to build your motion revision toolkit in 3 simple parts. First, we'll get the language right, the key words you just have to know. Then we'll get visual and figure out how to decode those graphs that tell the story of a journey. And finally, we'll get our hands on the equations you need to do the actual calculations. Let's do this.
First things first, the language. You see, in physics, words have really precise meanings, and the first big idea to get your head around is the difference between scalars and vectors. It might sound a bit technical, but it is the foundation for absolutely everything else we're going to talk about. So, let's kick off with distance versus displacement. What's the deal? Well, imagine you walk 500 meters all the way around a park, and you end up right back where you started. The distance you traveled is 500 meters. That's a scalar. It's just a number, a size. But your displacement, that's 0, a big fat 0. Why? Because displacement is a vector. It cares about the straight line distance from your start point to your end point, and the direction. Since you finished in the same spot, you haven't been displaced at all.
And you know what? This exact same idea applies to speed and velocity. Speed is your scalar. It just tells you how fast you're going. Say 30 meters per second. Simple. But velocity, that's the vector. It tells you the speed and the direction. 30 meters per second due east. Think about it. A car going in a perfect circle might have a constant speed, but its velocity is changing every single second because its direction is always changing. So here's the bottom line. Vectors have direction, scalars don't.
Right, let's move on to the second part of our toolkit. We're going visual. I can pretty much guarantee you will get questions on graphs in your exam. But don't worry, they're not that scary. They're basically just pictures that tell the story of an object's journey, and our job is to learn how to read that story.
First up, we have the distance time graph. This is probably the most common one you'll see. As you can tell, the y-axis shows the distance from the starting point, and the x-axis just tracks the time. This graph here shows a journey with a few different parts to it. Let's break down what each bit of the line is actually telling us.
Okay, decoding this is actually pretty simple once you know the one key rule. The gradient, or the steepness of the line, tells you the speed. So if the line is horizontal, it's flat. The gradient is 0, which means the speed is 0. The object isn't moving. If it's a straight, sloping line, it's moving at a steady, constant speed. And the steeper that line gets, the faster the object is going. Gradient equals speed. It's as simple as that.
Seriously, if you only remember one thing from this section, make it this. The gradient of a distance-time graph is speed. Burn that into your brain, remembering that one little fact can be the difference between getting a question right or wrong, and it's so often an easy mark just sitting there waiting for you.
But what about a velocity time graph? Now this is where things get a little more interesting, and it's where people can get caught out. Notice the axes have changed. We've got velocity on the y-axis now. And that means a horizontal line does not mean the object is stationary anymore. So here are the new rules for a velocity time graph. The gradient now tells us the acceleration. So a flat horizontal line means constant velocity, which means 0 acceleration. An upward slope, it's speeding up, it's accelerating. A downward slope, it's slowing down, decelerating. But wait, there's more. There's a bonus piece of information hidden here. The area under the graph actually tells you the total distance the object has traveled. So, 2 key things. Gradient is acceleration, area is distance. And that brings us perfectly to the final part of our toolkit, the maths. Sometimes you won't get a nice graph, you'll just get a bunch of numbers in a question. And for that, you need the right tool for the job. This is where the equations of motion come into play.
The first equation we need is the one for acceleration itself. It's simply how quickly your velocity changes. The formula makes total sense. Acceleration equals the change in velocity divided by the time it took for that change to happen. And please remember your units. It's a classic mistake to forget them. Acceleration is in meters per second /squared. Now, speaking of acceleration, there's one special number you just need to know. It's the acceleration caused by gravity. Here on Earth, if you ignore things like air resistance, any object that's falling freely will accelerate downwards at about 9.8 meters per second squared. This is a constant that pops up all the time in exam questions.
So, what happens if a question gives you velocities, acceleration, and distance, but doesn't say anything about time? Well, that's when you pull out this beauty.
It's the equation that links all those things together. And here's the best part. You do not have to memorize it. This equation is given to you on the official physics equation sheet in the exam. Your job is just to recognize when to use it and how to plug the numbers in correctly.
So let's pull all of that together into a super simple checklist for when you're in the exam. Step 1. Know your definitions. Can you explain scalar versus vector? Step 2. If you see a graph, the first thing you do is read the axes. Is it distance time or velocity time? Step 3. Remember what the gradient and the area mean for each of those graphs. And step 4, if it's a calculation, look at what information you have and pick the right equation for the job.
Okay, to finish off, here's a little challenge to test yourself. A car accelerates from a standstill to 27 meters per second, and it does that in 10 seconds. Using the toolkit we've just built together, can you work out its acceleration? And maybe even sketch what its velocity time graph would look like? Have a go. You can do this.